Good afternoon, everyone. Welcome to the fourth day of the Flatland workshop. We're very pleased today to have as our first speaker Hong Yao from Tsinghua University, and he's going to talk about exact quantum criticality, emergent supersymmetry, and emergent SO5 symmetry. So Hong, please.
All right. Thanks, Simon, for the introduction. First, I'd like to thank the organizers, Simon, Igor, John, and Hubbard, for the kind invitation. It's really my great pleasure to attend this workshop. Can you see my slides?
Yes, perfectly.
Right. Today I will discuss about exact quantum criticality, emergent supersymmetry, and emergent SO5 symmetry. Before I start the content of this talk, I'd like to thank the main collaborators involved in what I will discuss. They are Zhiqiang Li, a former student of mine, a postdoc at UC Berkeley, and just moved to Institute of Physics in Beijing as a faculty last month. Abu Hassan was a postdoc at Stanford University, so now is a faculty. As a faculty at Sharif University of Technology, and Chris Mendel, also a postdoc at Stanford, now a faculty at TU Dresden, and Saul Kajian, a former student of mine, now a postdoc at University of Maryland, College Park. These are two papers which will be the talk I will be based on. I believe that most of the audience are quite familiar with quantum critical point. A quantum critical point is a quantum phase transition at zero temperature by tuning a parameter in Hamiltonian. At a quantum critical point, the correlation length diverges, and there is emergent properties such as scale invariance, and the symmetry of the system at the quantum critical point can be enlarged. For instance, the system graphene at charge neutrality has emergent Lorentz symmetry and also scale invariance. And so there are many exotic symmetries such as supersymmetry and SO5 symmetry has not been discovered in nature. The main question we would like to ask is, can they emerge at quantum criticality in condensed matter systems? So this is the main theme of this talk. Here's the outline of this talk. First, I will give you some brief introduction to supersymmetry or SUSY and emergent SUSY in condensed matter systems. After that, I will discuss a quantum Monte Carlo study of the superconducting transition on the surface of a 3D topological insulator. From this quantum Monte Carlo study, we found evidence of emergent SUSY at the superconducting quantum critical point. The second part of my talk will be emergent SO5 symmetry at deconfined quantum criticality. So this is also based on a quantum Monte Carlo study of a fermionic interacting model on the honeycomb lattice, which has VBS to antiferromagnetic transition at some critical interaction strengths. From the quantum Monte Carlo study, we found evidence of deconfined quantum criticality and possibly emergent SO5 symmetry. In the end, I will summarize. Usual symmetries are bosonic symmetries in the sense that the statistics of the particle are not changed under the bosonic symmetry transformation. For instance, spin rotational symmetry, translation symmetry, tiny Boson symmetry, reflection symmetry. All these symmetries are a bosonic symmetry. They do not change the statistical particle. A fermion is still a fermion. A boson is still a boson after this symmetry transformation. However, SUSY or supersymmetry is a fermionic symmetry. The statistical particles are changed under supersymmetric transformation. A fermion is transformed to a boson and vice versa. In a supersymmetric theory, each particle has a corresponding superparticle. For instance, electron is a fermion. Its corresponding superparticle is called S electron, which is a boson. Photon is a gauge boson. Its corresponding superparticle is called photinon, which is a fermion. So there are some hallmarks of a supersymmetric theory. First is it is Lorentz invariant. In condensed matter systems, as I mentioned earlier, Dirac fermion or wire fermion at when the chemical potential is exactly at the wire point or Dirac point, which can have emergent Lorentz symmetry. So we will mainly consider systems with Dirac semimetal. So which is good for emergent SUSY or emergent other symmetries. Secondly, the number of Dirac fermions or Dirac fermionic mode should be identical to the number of bosonic mode. As I mentioned, each particle in a supersymmetric theory has a superparticle. So has a corresponding superparticle. So the number of Dirac fermionic mode should be identical to the number of bosonic mode in a supersymmetric theory. SUSY was introduced around 4 decades ago, attempt to solve many fundamental issues in particle physics. For instance, it was attempt to solve the hierarchy problem, why the mass of the Higgs boson is so small. The other fundamental issue is the grand implication, why the gauge coupling flow to the same coupling, the same constant at high energy. SUSY was introduced to attempt to solve these fundamental issues in particle physics. However, evidence of SUSY in particle physics is still lacking. So far, LHC experiments are elective in finding a supersymmetric superparticle. So the main question we'd like to ask, can SUSY emerge in condensed matter system or in tabletop experiments? There are already many theoretical proposals of realizing SUSY in condensed matter systems at low energy and long distance at certain quantum critical point. For instance, a number of years ago, to my student and I proposed to realize a 3+1 supersymmetric point at the pale density wave quantum critical point in the bulk of a 3-dimensional wire semimetal. So consider a system with 2 wire points in a 3-dimensional wire semimetal. If this system undergo pale density wave transition, namely the pairing occur between fermions within the same valley, so-called intra-valley pairing. And so the pairing has a finite momentum, so it's called a pale density wave superconductivity. At such quantum critical point, we showed that there's an emergent 3+1 dimensional supersymmetric supersymmetry. 4 years ago, and we proposed to, together with Joseph and others, we proposed to realize a supersymmetric QED on the one-on-one surface of a three-dimensional topological insulator. We believe that that was the first proposal of a supersymmetric gauge theory in condensed matter system. There are many proposals, theoretical proposals of emergent SUSY in condensed matter system. Here I list part of the proposals. Most of the proposals above are mainly from a perturbative renormalization group analysis. The question we would like to ask in this talk, can SUSY be verified by non-perturbative method? For instance, numerical exact quantum Monte Carlo simulation in microscopic models. There is a very interesting theoretical proposal of realizing SUSY by Tyrone Glover, Donna Shin, and Ashwin Vishwanas in 2014. They proposed to realize SUSY at the superconducting quantum critical point on the surface of a strong topological insulator. On the surface of a 3D topological insulator, there is a single Dirac cone. And if the system, if the surface of this single Dirac cone undergo a quantum phase transition, a superconducting quantum phase transition by tuning some interaction parameter U, for instance, by tuning the strength of electron photon coupling or attractive U, and the system can undergo a zero temperature quantum phase transition from this a single Dirac cone to a superconducting surface state across a quantum critical value of U. At this quantum critical point, they argue that the quantum critical point can have emergent SUSY, and this the surface Dirac fermion is described by the two-component Dirac fermion, the complex fermion, and the superconducting order parameter is a complex boson, is a complex order parameter, is a two-component boson, and the SUSY is between these two-component Dirac fermion and this complex boson. So this was argued from this perturbative RG analysis. And the question we would like to ask is, can this kind of SUSY proposed theoretically be verified at the superconducting quantum critical point on the surface Dirac cone of a 3D topological insulator from non-perturbative approach, such as sign problem-free quantum Monte Carlo simulation. So in order to simulate such a quantum critical point, ideally we would like to simulate a three-dimensional system. However, quantum Monte Carlo study of a three-dimensional system is quite challenging. So we would like to using quantum Monte Carlo to simulate similar quantum critical point, but in a two-dimensional system with a single Dirac cone. We know that there is a Fermion-doubling theorem, namely the number of Dirac cone in a two-dimensional local lattice model has to be even if the model respects time universal symmetry. So in order to regularize a single Dirac cone in a two-dimensional lattice model, so we like to use this kind of approach, namely we consider a two-dimensional lattice model with long-range hopping. So we consider this hopping model between spin up and spin down, but the hopping is not strictly local. Actually, at long range, the hopping decays in power law. It's a 1/r decaying hopping strength. So if we do a Fourier transform of this long-range hopping model, we get a perfect single Dirac cone. And this model respects time universal symmetry, and there is no violation of the Fermion-doubling theorem because of long-range hopping. actually, later we realized that the high energy physics similar fermion model was introduced, and this is called SLAC fermion because it was introduced by a physicist working at SLAC at that time. The SLAC fermion model can capture essentially all the features of a single Dirac cone. For instance, if we have a mass term, if we make a mass domain wall on this two-dimensional lattice model, and on this domain wall, so if we have a mass positive on the left and mass negative on the right, there's a domain wall between positive mass and a negative mass. At the domain wall, there is a chiral fermion, which is expected from a single Dirac cone. So this single Dirac cone model is good for our purpose. So the next step is to try to realize a superconducting quantum critical point and try to test whether SUSY emerge at the quantum critical point. So we consider this interacting model. So H naught is the SLAC fermion model, which has a single Dirac cone. On top of that, we consider attractive Hubbard U interaction. And this model is actually sign problem free. So we can perform a sign problem free quantum Monte Carlo, actually Majorana quantum Monte Carlo simulation to study this interacting model. So I won't go into the detail of this numerical simulation of this the so-called Majorana representation quantum Monte Carlo. For those who are interested, you can refer to these papers. And in the Majorana representation quantum Monte Carlo, and this model is sign problem free. And then we can use quantum Monte Carlo simulation to study this model on a system with large system size. So we can study the property at various U, and since for weak U, so the chemical potential is exactly at the Dirac point. So for weak U, the interaction is irrelevant because it's a Dirac fermion, it has a vanishing density of state. So all weak interaction are irrelevant. So we'd like to know what is the critical value of U beyond which superconductivity can emerge, can occur. So we study the structure factor of this S-wave superconductivity. Since it's on-site attractive U, we expect that superconductivity is on-site S-wave. So we study the structure factor of this S-wave superconductivity, and from this structure factor, we can, after the finite size scanning, we can obtain whether this superconducting order parameter is 0 or not. And when the interaction is less than the critical value of U, so there is no superconductivity. When the interaction is larger than U, the superconductivity can occur. From our numerical study, the superconducting quantum critical point is around 0.82 to 0.85. The unit of this critical U is bandwidth. And then, so this tells us that there is indeed a superconducting quantum critical point. And then we try to study the critical exponent of this superconducting quantum phase transition. From this, we know that the superconductivity, this superconducting quantum phase transition is likely to be continuous, since the order parameter beyond the UC term seems there's no jump. So we expect that this is a continuous phase transition, and then we track the critical exponent of this continuous superconducting phase transition, and this is the result we obtain. So the UC is a critical value from this. Here also the Binder ratio has a very nice crossing, also indicates that it's a continuous phase transition. Eta B is the autonomous dimension of the boson or the parameter, and eta F is the autonomous dimension of the fermions, and nu is the correlation length exponent. All these are obtained from quantum Monte Carlo simulation. I won't go into the details of this analysis. So I just want to mention that if this quantum phase transition features n equal to 2 SUSY predicted from this the paper by Tyler Glover et al. And so this 2 + 1 n equal to 2 SUSY actually the autonomous dimension of boson and fermion is known exactly according to this work. And first, the autonomous dimension of boson should be identical to autonomous dimension of fermion in a supersymmetrical theory. Moreover, the value for this particular supersymmetrical critical point is 1/3, which is known exactly from this work. And so this our numerical result is actually quite close to the theoretical prediction of 1/3, so which is good. Moreover, from the conformal bootstrap calculation, the correlation exponent is about 0.917. Our numerical result is also consistent with this correlation length exponent obtained from conformal bootstrap. So our numerical result are quite consistent with the exact or quasi-exact value of the critical exponent associated with n equal to 2 SUSY. So our quantum Monte Carlo simulation provide a strong support of an emergent SUSY at the superconducting quantum critical point of a surface Dirac cone in three-dimensional topological insulator. Although we didn't simulate a three-dimensional topological insulator, we simulate a single Dirac cone regularized on a two-dimensional lattice. We believe that the quantum criticality we obtained represent the surface single Dirac cone of a three-dimensional topological insulator. If such SUSY or superconducting quantum critical point is realized in experiment on the surface of a 3D topological insulator, how do we detect such supersymmetric quantum critical point? There are two predictions of this supersymmetric quantum critical point. One is the density state at the supersymmetric quantum critical point is proportional to omega to the power 4/3. The power 4/3 is computed exactly. And this is the first prediction. And the second prediction is was obtained by Joseph and William, is that the optical conductivity at low temperature is also known exactly from this SUSY, and which is quite different from the free Dirac fermion. So if we can measure the optical conductivity at low temperature, this is also another experimental feature of this supersymmetric quantum critical point. So after that, I will go to the second part of this talk, namely quantum Monte Carlo study of one-spun solid to antiferromagnetic transition on the honeycomb lattice. We try to see whether SO5 symmetry emerge at this putative deconfined quantum critical point. So what is deconfined quantum critical point? Deconfined quantum critical point was first proposed by Santiago et al. Around 20 years ago. So it's a quantum critical point violate a Landau criterion. If we have a quantum critical point, if we have a quantum phase transition between two broken symmetry states, for instance, one state break a spin rotational symmetry, so instance, the Néel state break spin rotational symmetry, the one-spun solid break the lattice translation and rotational symmetry. If there is a direct phase transition between these two symmetry broken state, Landau tells us that the transition is first order. However, this work tells us that the transition can be a continuous transition. It's an exotic transition. It's called deconfined transition because certain excitation at this putative quantum critical point are deconfined. For instance, spin-on deconfined at this putative quantum critical point, deconfined quantum critical point. And for this deconfined quantum critical point, there are works propose emergent SO5 symmetry in the sense that the Néel state has 3 component order parameters. The VBS state has 2 component order parameters. So at this DQCP, maybe the symmetry is enlarged to SO5. If SO5 symmetry emerge at this putative deconfined quantum critical point, from the conformal bootstrap, there is a bound on this critical exponent. For instance, the enormous dimension has to be bigger than 0.52, and 1 over nu is less than this quantity. So this bound are quasi-exact from the conformal bootstrap calculation. However, a previous quantum Monte Carlo study of this putative quantum critical point in many models, they didn't obtain enormous dimension which are consistent with the conformal, the result obtained from the conformal bootstrap calculation. So it raised a question whether such a DQCP can occur at the direct phase transition between Néel state and VBS state. So here we would like to study most calculation before bosonic calculation models, which are spin models. So we would like to see whether DQCP can emerge in fermionic systems, fermionic models. So we consider a model with a Dirac fermions has 2 Dirac cones, and for instance the graphene, and assuming that some certain model can have 2 broken symmetry state. One is antiferromagnetic state, which breaks the spin SO3 symmetry. The other is the Kekuli VBS state, which breaks the translation symmetry and rotational symmetry. And so we can have a unified view from the Dirac points. as I mentioned earlier, the antipragmatic order has 3 component order pyramid, and the Kekuli VBS order can be characterized by 2 component order pyramid, phi 1 and phi 2, and this the Neo order pyramid can be described by this from the fermion description can be characterized by this this order pyramid, and this Kekuli can be characterized by this order pyramid. So now if we integrate our fermions, we can obtain a nonlinear sigma model with a topological term, a topological West-Witten term. This appearance of the topological term is a hallmark of the Landau forbidden transition or deconfined quantum critical point. And it also conject to drive emergent SL5 symmetry. I noticed that there is also proposals of pseudo criticality or quasi criticality since the previous I mentioned the numerical result are not consistent with the result obtained from the conformal bootstrap, and there's some proposal of such a transition might not be a genuine critical point, but close to a quantum critical point. Here, I just want to use quantum Monte Carlo study to quantum Monte Carlo simulation to study a particular a model to see such DQCP and emergent SO5 can occur. So the model we started is this model, and again, so this is just the near stable hopping on a honeycomb lattice, a spin 1/2 fermion on the honeycomb lattice. We consider a repulsive U. So this is just usual repulsive Hubbard U. We also have this hopping squared interaction J. So this J, you can imagine that if we have some electron phonon interaction like SSH type electron phonon interaction, if we integrate out phonon, we can obtain such hopping squared interaction when the phonon frequency is large enough in the anti-adiabatic limit. So now I just consider this model as the starting point. And this is the phase diagram we obtain. So it has, for weak interaction, it has a direct semimetal phase. As I mentioned earlier, all interactions are irrelevant if they're weak. And this model has, for large U, it has antiparallel state. We know that. And for large J, for intermediate J, it has a VBS state, Kekuli VBS state. When J is large enough, it is also antiparallel state. And then we study the transition between the VBS and antiparallel state. We found that when U equal to 0, actually the transition is first order, not second, not continuous. However, when the U is in this range, and the transition, we found that the transition is a continuous phase transition. So there's a tri-critical point separating the continuous phase transition from this first order phase transition. The dashed line represents the first order phase transition. The solid red line represents continuous phase transition. So that's our numerical evidence for this continuous phase transition. Moreover, and I mentioned earlier, this is the bound obtained from the conformal bootstrap. The previous result obtained enormous dimension, which are not consistent with the result from the conformal bootstrap. For this model, we found that the enormous dimension, for instance, when U equal to 1, so we just change J, and the enormous dimension we obtained actually is 0.5 line, and actually which is consistent with the bond obtained from the conformal bootstrap, and although it's close to the bond, to the lower bound obtained from the conformal bootstrap, but consistent. Moreover, this 1 over nu are also consistent from the conformal bootstrap bond. For this model in this range, and we found that the critical exponent obtained are consistent with the conformal bootstrap, implying this quantum critical component might have emergent SO5 symmetry. Indeed, we found evidence of emergent SO5 symmetry. First, at the quantum critical point, at the quantum phase transition, we found that there's a U1 symmetry for this VBS autopyramid. So although
Hong, can I interrupt? You've had 35 minutes, so you now have 5 plus 5.
Great, thank you.
Good.
And for this VBS autopyramid, actually the autopyramid is the Z3 autopyramid because the lattice has Z3 rotational symmetry, but at the quantum phase transition, there's an emergent U1, namely the boson, the real component of the boson, and the imagined component of boson has this is the circular shape, the whole. And moreover, the spin autopyramid and the VBS autopyramid also has symmetry. So if we consider a two component, one component is the VBS autopyramid, for instance, the real. So if we consider the VBS autopyramid as the cosine theta and the antiparabolic autopyramid as sine theta, if emergent SO5 symmetry occur, and this anisotropy should be a 0 at the quantum critical point. Indeed, so if we compute such expectation value, and we found that when J, so we just fix U, change J, when J is around the quantum critical point, the 4.6, the black dot, this moment actually is very close to 0, which indicates that there's some symmetry between the VBS order and antiparabolic order, in the sense that we can rotate VBS order to antiparabolic order at the quantum phase transition. So from all this numerical evidence, we think we showed this quantum phase transition is probably a DQCP with emergent SO5 symmetry in 2+1D, which satisfies the conformal bound. Again, and this is a numerical study, the largest system size we compute is, I didn't mention here, is 24. So this is the best we can do for the quantum Monte Carlo simulation. Up to this system size, we found that the quantum phase transition between the VBS and antiparabolic state in some range of in the phase diagram, it is a continuous phase transition. Okay, so let me conclude with this remark. First, I introduced a Hubbard model with a single Dirac cone on the square lattice from quantum Monte Carlo study. SUSY was shown to emerge at the superconducting quantum phase transition of this single Dirac cone model. After that, I showed that from the quantum Monte Carlo study, a particular model, the Fermion-Hubbard model, the extended Fermion-Hubbard model on the honeycomb lattice has interconnect with base transition, and in some parameter region of the transition is shown to be continuous with emergent S5 symmetry. And we think that this probably the first numerical evidence of DQCP with emergent S5 symmetry in a fermionic model. Let me thank you for your attention.
Thank you, Hong. So
Thank you.
I think the chair is going to applaud you on behalf of everybody.
Thank you.
We have time for some questions. People can raise their hand or put something in chat. Lucas.
Yeah, so my question is, if for this second part, if you integrate out the fermions, you
Yes.
said something that you end up with some Wessel-Witten term, I mean, some nonlinear sigma model with Wessel-Witten term, right? So is this precisely the same theory that you get as for example, in these more older studies, such as those of Farkas group, or is it a different bosonic theory?
I think it's the same theory.
The same thing. So would you be able? I mean, for example, if you were able to study, I mean, to simulate this bosonic theory, would you expect the same kind of exponents? Yeah,
I think that's a good question. So for a particular, So here, if we look at the phase diagram, and so we see some region actually is the first order phase transition, some region is the second order phase transition, and so this, for instance, I mean, the low energy effective theory sometimes, I mean, for a transition, for instance, the transition. So there's a old saying, last thing stop a first order phase transition. For a particular model, we can always obtain. For a particular model, we can always obtain a first order phase transition at some parameter range. For instance, the Ising transition. Ising transition, we can also have a first order phase transition, right? So if the 5-force theory, if the coefficient in the 5-force is negative, and then we need to consider the 5-6 term. The symmetry doesn't tell you whether it's a second order or first order. And so if we found evidence of continuous phase transition, and it indicated that this transition can be a continuous phase transition.
So is your claim somehow that you just have found a very particular fortunate microscopic realization that other microscopic implementations have not found? I mean,
that's what it's my current understanding.
Okay. Yes. Nice. Thanks.
Joseph.
Thanks for the question.
Joseph, you have a question.
Yeah. So it was about this SUSY QCP. So I remember the optical conductivity. I remember you were interested in trying to compute it. So I was wondering whether you were able to compute it in quantum Monte Carlo. I remember it was difficult. I was wondering if there had been some progress.
Actually, this is a good point. So we were quite interested to compute that from Monte Carlo simulation, but the kernel operator is quite complicated because the model we have is a long-range hopping model. So we tried, but and then the student didn't finish that this first author, Zichang, and maybe in the future we will try to continue on that.
Yeah, and I guess if you were to sort of use this method where you kind of integrate out the bulk, then you get this non-local effective action in time. I guess that becomes also very computationally difficult, right? If you wanted to use like,
yeah.
Okay.
I see. So yeah, instead of just using the SLAC fermion, you want to probably integrate out the bulk to get the effective. Yeah, that's another direction. Yeah.
Okay, but it's probably computationally quite demanding. Right?
Yeah. It's quite complicated. Yeah, computational. Yeah.
This is a fascinating area, I think. But we have no more questions at present. Hong is able to stay late enough to be in Gathertown following this session, and I invite people interested to pursue further discussion then. But thank you very much, Hong, for a really great talk.
Thank you all.
So now our next speaker is Andreas Wipf. Are you ready to go, Andreas?
I'm almost ready, yes. Can you see it now?
Yes, I can see it. Shall I introduce you? Here, that's better.
No.
Okay, so Andreas is going to tell us about phases and the critical flavor number of the three-dimensional Turing model.
So, thank you. It's really a pleasure to give this talk at this interesting meeting at the interface between, if you want, condensed matter physics via quantum field theory up to particle physics. It's exciting years, I would say. So I want to talk a bit about some problems we encountered by studying three-dimensional Turing models. And actually, it so happens that to understand the Turing model is much harder than to understand the Gross-Level model. And I hope to make clear why this is the case. And still, after lots of efforts from many sides, we don't completely agree on the overall picture of what happens in these systems. Okay, now we will actually use this nicely fits to the previous talk. We will use SLAC fermions where you can implement all, I repeat, all global symmetries and also parity, of course, besides space-time symmetries. So it's very important to discuss which type of models and what are the symmetries of the model. And it turns out it really depends whether the fermions are 4-component or 2 components, or if you have 1 or 2 Dirac points, the results depends on the choice. Then I will a little bit talk about fermionic determinant. Then in particular, I will present the lattice simulation. This is the main part of my talk. And we'll discuss about the critical flavor number. And I will explain what this critical flavor number is. The last point probably is beyond the time limit. Okay, actually, maybe I can flash this part, which just should again highlight that we are working, if you want, in the interface between different fields in physics, which were separated up to some years ago. And also this, you essentially know everything what is written here. Here we'll concentrate on 4 Fermi theories in 3 space-time dimensions, which are renormalized in the large N expansions. And the question we will look at is about UV fixed points in the Turing channel, so to say, in the Turing model. We will use a lattice approach. And this has been used in the past by several groups to discuss the critical behavior, critical exponents, the mass spectrum, even study this model at finite fermion density, study inhomogeneous condensates, and so on. We will again, as I told you, talk a little bit about the sign problem, and this depends a bit on which type of models you're looking at, of course. And we will discuss results obtained with chiral fermions on the lattice. Okay, so let's just a little bit discuss the 2 types of model, and we will discuss in following. The first, if you have 4 components of Dirac spin-offs, they're really from a reducible representation of the 3-dimensional Lorentz group, and they naturally arise in solid state physics when you have an even number of Dirac points. So the capital gammas are the four-dimensional gamma matrices. And of course, there's always a fourth gamma matrix, if you think about in 4 dimensions. So besides these 3 gamma matrices, you have gamma 4, and of course, in 4 dimensions, the gamma 5, so there are 2 additional anti-commuting matrices. So you have 2 notions of chirality. Of course, it's not really chirality. There is no chirality in the strict sense in 3 dimensions. It's more a flavor rotation, but it's called chirality in this context. So then we study models with NF flavors. And the free model has this huge symmetry. It has a global 2NF, where NF again is the number of 4-component Dirac spirals. Symmetry, in addition, of course, we have parity. These are the main symmetries I'm interested in this talk. So if you add now a Turing interaction, current interactions, this is compatible with this symmetry of the free theory. So we still have the same U2NF, 2NF times Z2 symmetry. Okay. Now, if the system would be able to form this condensed psi, which is actually the scalar, then you would break the U2NF to a UNF to a UNF, which is usually called a Turing breaking. It's the usual breaking considered in the Turing model. But of course, in principle, it could also form a sort of a staggered type condensate. It's given by psi bar gamma 4, 5. Gamma 4, 5 is a product of gamma 4 and gamma 5. And this is a pseudoscalar. And then actually only parity would break, not the U2NF. So there's no something like chiral symmetry breaking, just parity would be broken. We should contrast this to the model built on the 2-component spinors, the irreducible models. So now the gammas are 2 times 2 matrices. And so there is no notion of chirality in this model. And the Lagrangian is again the same. We have NF number of flavors. And now this model has a UN symmetry and parity, of course. And here the psi bar psi in this model is a pseudoscalar. And it just breaks parity, but not the global flavor, not the global flavor symmetry. And so the number of irreducible flavor I denote by N irreducible, the number of reducible flavor I denote by NF. So what is the relation between the two? Now the 4-dimensional gamma matrices necessarily contain both irreducible representation of the 2-dimensional gamma matrices. It's easy to prove. For example, you could choose this representation where the 4-dimensional gammas are given by the Pauli matrix times the 2-dimensional gamma matrices. And then a 4th spinor decomposes in this way in 2 spinors. And if you write down the kinetic term, you see there's a relative minus sign between the 2 flavors. It just comes from the sigma 3 in this representation. Okay, now you can get rid of this minus and arrive at the standard kinetic term by making this transformation on the spinors. If you do that, then you get a standard kinetic term with a plus sign. But the condensate psi by psi goes into the staggered condensate, and the previous staggered condensate goes into the usual what you would write from a condensate. Okay, this actually explains this mismatch between scalar and pseudoscalar in the 2 models seemingly. Okay, the rest is again standard. We get rid of the Wolfram term by a Hubbard-Stokanovic transformation, introducing a vector field. And in the following, lambda is essentially 1 over g squared. So strong coupling means small lambda and vice versa. Then we can integrate, or we can try to integrate over the fermions. And we get this effective action containing the fermionic determinant, and which contains the vector field. Okay, now the reducible, in the reducible representation, the Dirac operator is just sigma 3 times the one in the reducible one, which is Hermitian, at least it's a continuum. And you see there is no sign problem, obviously, because this is the square of the determinant of this one. So for obvious reason, there's no sign problem in the reducible Turing model. And actually, if the mass is 0, then the reducible model with NF fermions is equivalent to the reducible model with 2 NF 2-component fermions. The same is not true for the massive model. It's true for the massless model. Okay, now the large N limit can easily be worked out. It's actually a boring theory. We just work out this determinant, and In the large n limit, you can use the saddle point approximation, and if the saddle is attained at a constant vector field, you can just work out the additive potential. It's boring. It's just a quadratic function of the auxiliary field, plus an additional term which depends on the mass and the temperature maybe. But what you see, that if you take the derivative, which gives the condensate, it's obviously 0 when you remove the mass. So in the large n limit, there is no chiral condensate. On the other hand, for one flavor, irreducible flavor, two-component flavor, we know that the Turing model is equivalent to the bosonic model, which is known to have a chiral condensate. So we have the situation that for one irreducible flavor, there is a chiral condensate. For infinite flavors, there's none. So we expect there should be a critical flavor number, NF critical, below which the system can be in a broken phase, and above which there is no broken phase. So the question is, what is this critical flavor number? And there's been many works in the past. So this diagram shows the situation up to 3 or 4 years ago. 4 years ago. And you see results from the Schwinger-Dyson approach, from 101 NF expansion, functional normalization group in green, lattice with staggered fermion, and the first attempts on the lattice with domain wall fermions, actually by Simon. And okay, and you see there's almost everything was possible between 2 or no, actually before domain one between 3 and infinity, so to say. It was just very hard to pin down this critical flavor number. Okay, now the situation has changed the last 3 years, and actually in a certain sense it has improved considerably since use chiral fermions. So there's the calculation we have done with chiral SLAC fermions. What we claim that if the number of two-component flavors is even, okay, so there's an even number of Dirac points, then there's never a breaking. Okay. But there was some work actually already 4 years ago. And 2 years ago, we've zoomed into the n equals 1 and allowed for did simulation with a fractional number of flavors and came with a number of 0.8. So in other words, for n equals 1, 2, 3, there is never a broken phase. There's no, at least a phase transition with an order parameter. Now, for an odd number of irreducible flavors, you can have breaking up to, up to the number of flavor equals to 9 irreducible flavors or 4.5 of reducible flavors. Now, roughly at the same time, Simon and his collaborators simulated this, our same system, calculated condensate, spectrum of the Goldstone bosons, and so on. And by this domain wall formulation, at least the newest result is that this critical flavor number should be between 1 and 2. It certainly should be bigger than 1 and should be smaller than 2. So you see that's, we come closer. We don't agree yet, but okay, then there also has been an FRG calculation by Hugo Gies and his collaborators, in which they allowed now for momentum-dependent couplings, and what turned out that the critical number came down, and it's actually it could be compatible with n critical less than 1. Okay, so sort of the different methods sort of converge that the critical number is around 1. We would say below 1, maybe a little bit above 1. So we use chiral SLAC fermions. So let me, maybe not everybody knows what it is. It's very simple. I mean, in the continuum, we know that the derivative in Fourier space is just multiplication of the momentum. So you just take this definition on the lattice. You just define the derivative as the multiplication with the lattice momentum of the Fourier transformed wave function. If you transform back to X space, then the derivative is non-local. It's long range hopping terms. Now, one little bit more technical point, if you have periodic boundary condition, you need an odd number of sites. And if you want to have antiperiodic boundary conditions, finite temperature boundary conditions, then you need an even number of sites. And we use these SLAC fermions almost now, I don't know, 12, 13 years, and optimize the code and apply this, this type of fermions to many, many systems. I should say, don't apply it, don't use them for gauge systems. They would fail. But for non-gauge systems, scalar field, actually applied it to a supersymmetric Yukawa model, a SUMINO model with n equals 2, 2, and 1, 1 in various dimensions, extract critical exponents and phase transitions and so on. So got high precision numbers for the critical coupling and critical exponent. And maybe you have yesterday seen the post of Thomas Lang, where they also use the SLAC derivative in the Hamiltonian formulation to extract very accurate critical number for the critical exponents for the Gross-Neveu model. Now, what is the advantage of these fermions? First of all, I mentioned at the beginning, this symmetry, which is very essential for our studies, is exactly implemented on the lattice, including the parity, at least on the hypercubic lattice. The d mu, this derivative, which I explained a minute ago, in space is real and antisymmetric. It's a real and antisymmetric matrix, which means that the Dirac operator is an I is Hermitian. That's very useful. Typically, there are sign problems on the lattice which you don't have the continuum, and they are due to the fact that this is not true. Well, here we have the same property as the continuum. Now, the auxiliary field in our case is non-compact site variable. It's not a gauge field, which is an advantage. We don't have any doublers, so we don't need any routing. And actually, the SLAC fermion also, they are long range. You know, if you optimize the code, it's very cheap now. It's almost as fast as naive fermions. It's faster than Wilson fermions now in our code. So it's very efficient. Now, there are disadvantages. These fermions are non-local. I already mentioned, don't use them in gauge theories. You would fail. You couldn't reproduce the anomalies. But we understand why, and we could prove that these problems are not present in the field theory, which we discussed today. Okay, now, if you have an even number of irreducible fermions, I showed you there's no sign problem. It turns out that even for 3, 5, 7, where there could be a sign problem, in practice there is no sign problem. That's just a result of the simulations. For one irreducible fermion, so if you have one Dirac cone, there is actually a severe sign problem. But we developed analytically a dual formulation that's mostly due to Björn Wellegehausen and Julian Lenz. A very beautiful dual formulation, which is actually very simple to Scheele's fermion back approach, but it's essentially transported his approach to SLAC fermions. So we have three-dimensional lattices with these lattice sites. We use rational hybrid Monte Carlo, certain number of stochastic estimators. We of course check for finite size effects, and at the end, then we were interested in the critical flavor number near 1. So we then finally zoomed into this domain of flavor numbers. More comes later. Okay, so this is more not so important for the simulation, but it was very important for us for the analytic studies. So this Fiat's interaction term, this current interaction, so psi, this capital psi is a column of NF irreducible flavors, can be written by a Fiat's identity into this tensor and scalar interaction, which again can be bosonized by introducing auxiliary fields. In this case, it's a scalar field, a real scalar field, and a tensor T, generator of SUN. Now, we see from this form of the Lagrangian, you immediately get the Dyson-Schwinger equation, which tells us that the expectation value of this tensor field is related to this expectation value of the bilinears. Now, this model has inherits a symmetry if you transform this tensor field in this way, in the joint representation. So you see that the expectation of T is an order parameter for the spontaneous symmetry breaking, because again, its expectation value gives you this condensates you, these bilinears. Now, this problem we never simulated because it is a hard sign problem. It's actually, it's funny, you start with a model which has a Hermitian Dirac operator, has no sign problem for an even number of flavors. You make a Fierz rearrangement, you get this problem, complex determinant with a severe sign problem. Or if you go the other way around by Fierz reordering, you get rid of the sign problem. It's sort of an interesting observation, I would say. Okay, so then we can set up a dual formulation. There's no time to discuss that, but the main variable in this dual formulation is a lattice filling factor K. This is a spin field which actually counts the powers of the Fermi fields, which is between 0 and 1 and not 2 because of Pauli blocking, the Pauli principle. And out of this KAB's XI tells you roughly what is the occupation number. At site X, spin I and AB are flavor indices. And then you sum over the indices, and K is then the lattice filling factor, which tells you on the average, if it is near 1, you have Pauli blocking. If it's 0, there's almost no fermions around. Okay, then this was really the hard work, and it was almost a PhD thesis. You can calculate the effective potential, can expand it in a power series, and actually it's a polynomial in this TC. So TC was this tensor field. Actually, it's only the diagonal part of it because we have this at the adjoint action on the symmetry. So it only depends on the Cartan piece. So this is an exact relation where these coefficients A can be expressed as expectation value of fermionic powers of fermionic bilinears. Okay, so this is again an exact relation which you got from the duality applied to the tensor formulation of the theory. So then we can calculate this expectation value in the vector simulation, in the vector field formulation where we don't have a sign problem. And then we can plug it in and get this polynomial and can work out the effective potential. And you can now analyze this one, and it turns out that the symmetries of this potential have a very simple form. They are diagonal matrices with only 1s and -1, a certain number of +1s and -1, and some modulus, essentially X. And of course, you can always permute the entries. This is just the action of the while group. And so the minima of the effective potential is just characterized by n+, so if you want n-, because the sum of the two is just the number of flavors. So depending whether the number of flavors is even or odd, the n can take these even values or odd values. Okay. Now, you see, we can probe now in this tensor formulation, we can probe all this condensate in the different directions, the directions given by this TC. We can look for the breaking going from U to NF or N irreducible into UN plus, UN minus. The N plus and N minus vary between 0 and the number of flavors, and the sum is always given by the number of flavors. So you have different symmetry breaking patterns. For example, if the number of flavors is even, then we can assume an N plus can be N minus. Remember, and number of flavors is N plus plus N minus. For example, this case where both are 4. And then we have the breaking, let's in this case, a U8 to U4 cross U4. This is a Turing channel, the Turing breaking. Or if Fn is maximum, then N minus must be 0, and UN to N goes into U2N. So there's no breaking of the chiral symmetry, just parity breaking. This we call the Gros-Neveu channel. Okay. Now we can actually work out this effective potential in the strong coupling limit analytically, and just actually the Monte Carlo simulations are not much different, amazingly. And then you see how it looks like. Here we have the effective potential for one flavor, and in this case, n can only be 1, equal to n plus. And that is how it looks like. And you see, you would say you have spontaneous symmetry breaking in the Gros-Neveu channel. Okay, so this means in this case, yeah. Okay. Now let's look at this n equals 2. Then we have the possible going into U2 goes to U2, that is the tearing channel, or the U2 goes into U1 cross U1, the crossover channel. Oh, I mixed it up, I guess now. Okay. And you see the tearing channel is below the crossover channel. And now look at this figure. N equals 1, 3, 5. The odd one look qualitatively different to the even one. 2, 4, and so on. So what you see that if the number of irreducible flavors is odd, then chiral symmetry is always broken in the strong coupling limit. Whereas if it's even, the chiral symmetry is always unbroken in the strong coupling. So look at this picture. Well, maybe n equals 4. So the minimum is the origin, and you would say there's no breaking. N equals 2, that is 1 reducible flavor. That's a tricky point. And you see the tearing channel is very, very flat, and it's not obviously whether there is breaking or not. Okay, now we have done the same now with Monte Carlo simulations. This is shown here for four irreducible flavors, and the second two figures are for 5 irreducible flavors. And amazingly, it's almost the same, the conclusion as the strong coupling limit, that here we get in the crossover channel for n equals 5, we get symmetry breaking, and that is actually a stronger coupling, and on the right is a weaker coupling. So there would be a phase transition from the left to the right figure. Now above you see n equals 4 for of the Monte Carlo simulations. These are jackknife errors, of course, what you see. There is no symmetry breaking. Okay, now so we would claim now that there's well, we have the similar figures, of course, for the other flavors. So there is no symmetry breaking for the reducible models, and there may be there's symmetry breaking for the irreducible model. And actually, what you find if the number of irreducible flavors, the odd number is getting too big again, there's no symmetry breaking. But there's one problem. It turned out that there's an additional phase transition, which is what we call a lattice artifact. Now, what it really is, it's the following. And people who do simulation at very large fermion density, they know that if the chemical potential is too big, we get Pauli blocking on the lattice. That, you know, all states are filled, and that is happening here as well. In the strong coupling limit, the K, remember, it's a filling factor. K equals 1 means all lattice sites are occupied. Well, we have Pauli blocking. So you see lambda, small lambda was strong coupling. For small lambda, independent of n, again, n goes from 2 to 11, the number of irreducible flavors, the filling factor goes to 1. For weak coupling, it goes to 0. And actually, we can derive by the dual formulation a beautiful relation between the average filling factor and this 4-point function, the current correlator. Okay, so now this is a little bit worrisome that we have Pauli blocking for strong coupling. And actually, if you analyze now the derivative of this filling factor, which is a susceptibility, it's actually a fermionic 8-point function, then you see that we get you know, sort of singularities. It's hardly to see, and namely, these are the curves for different volumes here. I didn't write it down. I guess this was 16 and 24. And the lines, they cross here. Okay, for the filling factor. And at these crossing points, the derivative of K with respect to the coupling, which is a correlation, is a susceptibility, has a dip. And with increasing volume, the dip is getting deeper and deeper. So we associate a phase transition with this would-be singularity. And then we, using different methods, we can calculate the critical coupling for this phase transition. But this is not a phase transition of the continuum model. This is a phase transition of the, we would say in field theory, lattice artifact, which actually may be interesting on in a solid state, because, you know, there you don't make the continuum limit, of course. And so this critical coupling decreases with the number of flavors. And now what you have to look, what we did, we looked at the curvature of the effective potential calculated in this Monte Carlo simulation at the origin, x equals 0. X was the modulus of this auxiliary field. Okay, so this is then identified with the condensator's minimum. So we look for the curvature, and if this curvature is positive, we would, at least this transition is second order, would say there is no broken phase and vice versa. And we can do this looking in the different directions for the cross-Neveu channel, the Turing channel, and all the other channels, all the symmetry breaking patterns, which we can obtain with this tensor formulation. And look, for example, here is the figure on the left. This is for two irreducible flavors. So this would be n equals 1. That's a tricky point where the different formulations don't yet agree. So we see this is a curvature of the effective potential at the origin in the different directions of breaking. And the most dangerous direction is a Turing breaking from U2 to U1 cross U1. But we are only allowed to go look at the right of this bar, because on the left we have the lattice artifact phase. This gray bar is this critical coupling, and we can only interpret this result, at least for continuum model, to the right. Okay, and it's from this figure almost clear that it's always positive, the curvature, so we would claim there is no broken phase, and even more for 4 flavors on the right. It's different for the odd number. For example, here we have 3 flavors, and you see the curvature. Oh, sorry. You see that the curvature becomes negative to the right of the critical coupling, where we run into the lattice artifact phase, and the same is true for 5 flavors and so on. And what we conclude is this is always the case if the number of irreducible flavors odd is less than 9. Okay, so this is again the picture. So the red one is the lattice artifact phase, and the green one is the parity breaking phase. It's a Gauss-Neveu channel, and so we have a parity broken phase for 1, 3, 5, 7, and maybe 9 flavors. Okay, so intermediate conclusion. So we see that the staggered fermions clearly fail because they predicted that the critical n is of the order of 6.5, 6.6. So domain-wall fermions favor a critical number between 1 and 2. And we would say that for 1, even for 1, there is no breaking of spontaneous breaking. So then, since there was this discrepancy, we decided to zoom into n equals 1 and study the models at n between 0.5 and 1.1. No, okay. And we looked at 25 different numbers of flavors. And in our algorithm, we can actually assume that the number of flavor is a fractional number. But we have to, I should tell you that we took the parity invariant continuation to a fractional number of fermions. We looked at different observables, chiral condensates, the mean spectral density, the masses of the light mesons, the Goldstone spectrum. The same was actually done by Sun before us in the domain wall model, and susceptibility. Now the problem is that the condensate if you directly measure the condensate, you get 0 for the massless model for any value of the external field. You don't have to average over the external field. So we did a simulation for small fermion masses, and turns out that a good parameterization is a mass is a fixed number of 0.1, 0.05 divided by the size of the system. So in the thermodynamic limit, this mass goes to 0. We had this little trigger current probe for the broken phases. Simon, how much time is left?
You've had 32 minutes, so I was going to interrupt you in another 3 minutes.
Okay, well, you don't.
Now I won't.
Okay, good. So let's now a little bit zoom into this region of 1 flavor, and recall that the reducible Dirac operator can be written in a certain representation as there should be a sigma 3, of course, times the irreducible 1, plus a little mass term. And again, to come from the reducible to the irreducible, you had to make this change of variables, which introduced sigma 3. So the 2 irreducible flavors have a different sign of the mass. And that's actually necessary not to break parity. Okay. And this mass is its trigger mass. Okay, and then it's easy to show that the effective action by this form of the Dirac operator can be written as m squared minus the irreducible Dirac operator squared. And of course, again, you see that there is no sign problem needed. Now we look for this order parameter, which belongs to the Turing breaking, which we know is a dangerous direction. So we look in this formulation of the staggered condensate, which does not break parity. And a little manipulation, Fermionic integration shows you that this can be written as an integral over the average spectral density, where maybe for a given auxiliary field, the spectral density is defined by this equation. So it's just, if you want to calculate the trace of a function of the Dirac operator, it's done by the spectral density. And the average one is, you also have now to average this. Oh, there's a row V of E missing on the right-hand side. So you have to average this one over the auxiliary field. And this gives you the one which enters this relation, which is a sort of a Banks-Kessler relation for this condensate. And you see that there's this mass in front of the very typical for the Banks-Kessler type relation. So the question whether the condensate can form is a question of how this average density, spectral density, behaves for small energies. So if this, goes to 0, for example, you immediately see that you can never have a condensate. So what I show you here is this spectral density, the average spectral density of the Turing model, the reducible Turing model, here for one flavor, now reducible flavor, and here for 0.8 flavor. And you can see the spectral density of different volumes. And you see if you increase the volume, look at the second figure, the yellow one is a small volume, very small volume, actually 8, then 12 cubed essentially, and then 16 cubed. You see how the spectral density accumulates at the origin. And that is the usual argument in Banks-Kessler to argue that there's a condensate, in this case for n equals 0.8. Whereas there should be no condensate for number of irreducible flavor, reducible flavor equals to 1. That's the first indication that, again, that it's below 1. It must be probably between 0.8 and 1.0, the critical flavor number. Now, the next we studied was the Goldstone spectrum. And as I mentioned, it has been done by the van Waal fermions in the bulk formulation. And Simon concluded that the critical flavor number should be bigger than 1. So what do? We take the mesons, study the masses of low-lying mesons. There are 2 scalars and 2 pseudoscalars, and they are given in the reducible notation by these 4 interpolating operators, where gamma A is gamma 0 and the 3 polymatrices. And then we integrate over space and project onto the 0 momentum part, and then we get these interpolating operators depending on the Euclidean time. Note that O3 is just a chiral condensate, and O0 is the would-be parity condensate, which is 0 in this theory. Okay. So then next, that's sort of standard. We look at the correlation matrix of these interpolating operators. And due to the, again, to the SLAC fermions, which inherits all symmetries of the continuum model, we can prove that this correlation matrix is diagonal. Okay, now if the U2 is unbroken, now I'm looking for 1 flavor, then we expect 1 singlet and a triplet. So we expect that 3 masses must be the same. Whereas if we have spontaneous symmetry breaking from U2 to U1 cross U1, we expect 2 Goldstone bosons. So 2 masses should be equal. And actually you can identify the operators, interpolating operators O1, O2, that they belong to the Goldstones. Now here's the 2-point correlation function, and then we extracted the masses here. So the left-hand side is n equals 1, the right-hand side n equals 0.8. So the right could be in the broken with Goldstone, and the right probably in the symmetric phase without constant bosons. And just look at the masses. So M11, 15 just means different lattice size. So let's look at the larger lattice. And the evening got the excited states, but let's look at this, the third row. So you see if there's no symmetry breaking, then indeed C1, 2, you can prove that C1 and C2 are the same. Even on the lattice without doing any simulation by symmetries, and that they are essentially the same. So that confirms that we have three masses, probably a triplet, U2 triplet, and certainly the other particle is much heavier, CC given by C2, C0. And then below you look at C1, 2 has the same mass, but C3 is much heavier, and actually C0, which I didn't plot, we could even not dissolve because the lattice was not fine enough. It's even more heavy. Okay, so clearly the spectrum, the second is a constant spectrum, that's the first one not. Again, we conclude. Now comes the last point. Remember we had this filling factor and its derivative with respect to inverse coupling. You can prove that this is given by this 8-point function, or if you want the 4-point function of the current or the 8-point function of the fermions. Now, we couldn't simulate the 8-point function. The noise was, of course, much too big. So what we did, the K, we have a very good handle because using as a dualization, we know the expectation value of the filling factor is given by the expectation value of the bosonic action, which we can easily calculate. So we took a numerical differentiation here, use this formula to calculate the susceptibility. Of course, we could discuss how to numerically differentiate, and we tried many ways to do it. Okay, so what you see is then roughly the following. The susceptibility is shown here on the left for 3 different number of reducible flavors. N equals 1. This is this sort of, what is this? Well, anyway, N equals 0.7. I think we wanted to start at this yellow. There's 1 dip. Now, if we increase the number of flavors to 0.8, you see a second dip develops. And if you go further to 1.0, so we see 2 dips. This is on a rather small volume. And then we did a volume study on the right for N equals 1. And of course, again, we see these 2 dips. So what you see is this monotone decaying curve. This is just the filling number. And what you see is the susceptibility with these 2 minimas. And we studied the volume dependence to extrapolate, of course, to large volumes. And it's clearly sees that we have 2 singularities developing in this susceptibility. So here is now the phase diagram near one flavor. So one flavor is here on top. Here on the left, we have the lattice artifact phase transition, which is now well separated from the second point where the susceptibility has this dip. And then you decrease the number of flavors, and at roughly 0.8, 2 phase transition meet. And below this, you have now this spontaneous broken phase, as we have seen. Okay, so this second phase transition, where this was a big surprise to us, and we still don't really understand what it means. It's a sort of an interaction-driven phase transition without order parameter, we believe. But we didn't really continue so far to study the nature of this phase transition. Okay, so again, there's spontaneous symmetry breaking only for n equals roughly 0.8, and above that there's none. But there may be this additional phase transition which is not understood up to now. Okay. Let me summarize a little bit this part. So I have shown you the results of simulation for the 3-dimensional 4 Fermi theories. With SLAC fermions, I showed you the result for the Turing model where the critical flavor number was in the focus of our simulations. We also have simulated Gauss-Neveu to calculate critical exponent, the Gauss-Neveu completely different reasons to study inhomogeneous phases. And we use the SLAC derivative, where we always implement the correct symmetries. For many models, we have no sign problem. And if there's a sign problem, we can use a dual formulation to handle the sign problem. Okay, now we claim that there's no, at least with the SLAC formulation, which has all continuous symmetry, there should be no spontaneous symmetry breaking for all reducible models, the one with 2, 4, and so on, Dirac points. And if you allow for rational number of flavors, it should be 0.8. I mean, I showed you one way to determine that by looking at the phase diagram. We also looked at different observables, and we produced two numbers. One was 0.78 and the other was 0.80. Okay, now clearly the choice of the fermion space is relevant in such a strongly interacting system. Staggered fermion give clearly different results to domain-wall fermions and SLAC fermions. Domain-wall fermions and SLAC fermions may converge in the future. We don't know. Maybe Simon want to comment on it. He looked a lot into that. There is parity breaking phase transition with order parameter, but only for the, if you want, unphysical number of flavors below 0.8, where there's no local quantum field theory. We have probably detected a new phase transition without order parameter. And again, the symmetries of the lattice fermions, we have learned, is very essential for this strongly coupled system, not to end up in the wrong universality classes. But still, there's this little discrepancies between SLAC and domain-wall fermions. Okay, just last 2 or 3 comments. I'm not talking about the T, of course, for time reasons. In the last 2 years, we were mostly interested in inhomogeneous condensates at finite density. There's a beautiful story. If you take the Gaussian model in the large N limit at finite chemical potential and finite temperature, there's an interesting phase diagram. Namely, there's for large densities and low temperature, there's a phase where the condensate is a modulated condensate, a space-dependent condensate. So there's a breaking of translation rates. Okay, which seems to invalidate many contradictions with many no-go theorems. So the question was, is there such inhomogeneous phase for finite number of flavors? And or if there are even inhomogeneous condensate in higher dimensions, 3 dimensions investigated, or hopefully in 4 dimensions. This is interesting for people working on the QCD phase diagram, because one hopes to have such, well, there's some hope that there may be some inhomogeneous condensates in QCD, large densities, for example, in neutron stars, because this model, at least the chiral sector, is described by 4 Fermi theories. So we look at interacting fermions in external fields. Is again a different story, because here the SLAC fermions seem to fail. They do not, but it's much more time consuming now, and actually we implemented domain-wall fermions to treat these systems. And we haven't started it, but I'm personally very much interested in studying condensates and their critical behavior for rotating Fermi liquids. Okay.
And Andreas, you're really eating into everyone's coffee time now, I'm afraid.
Oh, I'm sorry. I should stop here, so I leave all the rest. Okay.
I agree with you that inhomogeneous condensates are interesting.
Yeah. No, this was anyway an appetizer. That was all now. So thank you very much, and sorry if I overtook too much time.
Thank you so much.
Mm-hmm.
I guess we have time for some questions. Rajamani, would you like to ask a question?
Hi, Andres. Very nice.
Hello.
So you mentioned that when you look at it from different fermions like SLAC and domain wall, there's a difference. But I also want to point out, which you know obviously, that you use a contact interaction and you don't treat it at all as a gauge field.
Yes.
But Simon has a point split. And so it's a gauge field, guaranteed that it is non-compact, but it still has the properties of a gauge field.
Mm-hmm.
I'm wondering if that also has an effect in addition to having different fermions. The reason why I'm asking this question is, if Simon did odd number of fermions, I would assume that he will induce a Chern-Simons term, which you will not.
Okay, let me try to comment. So I agree, it's not the same. And actually, Simon himself commented on that in his paper, that the discrepancy may be explained by this different treatment of this auxiliary field. To your second question, Simon, correct me, but you always study the reducible fermions.
Yes, he does.
Parity...
But you study both odd and even, so.
Yeah, but he only used in my language the even number of irreducible flavors. I used odd and even. And actually, we of course, if we include the mass, then we get this anomalous term. And if you would have a gauge field, there may be a leftover. Now you can do a little calculation. You can, in the continuum, you can allow a vector field, which is not a gauge field. Okay, switch on a little mass, calculate the effective action, and remove the mass. And you're left with a sort of a Chern-Simons type term, irrespective whether the V is just a vector field or a gauge field. Okay. So there's breaking of parity, independent how you treat this extra field, as a gauge field or not. You know, it's a question about the determinant.
But the parity breaking is qualitatively different in the sense there's a severe sign problem coming from.
Yes. So let
me
me
I'm wondering if that also plays a role in the difference in the critical.
Yes. I think this is a deeper reason that if the number of irreducible flavors, we may have trigger a parity breaking, and for n even not. It's just built in, it's parity symmetric. I agree completely, yes.
So, and finally, I would like to comment, you know, my son is very much interested in football. He was very upset that Germany lost. For some reason, now he doesn't want England to win.
I can't allow this discussion. Lucas, time for a quick question because we're keeping people from their coffee.
Okay.
Okay. A quick question on the on this effective potential. I mean, that is, if I understood correctly, a strong coupling result, and then compared with Monte Carlo simulation.
Yes.
So why do you not see the artifact phase in this strong coupling expansion?
Yeah. Well, so what if you compare it, this is the strong coupling, huh? Let's, for example, look at n equals 2, and this would be the left one here, right?
Yes. So strong coupling with small lambda, right? Is that right?
Small lambda, yeah.
Yes.
So, lambda going to 0 actually.
Yeah.
So let's compare here you can see my pointer, the n equals 4. This is a strong coupling, and you should see it goes from -2 to 2, this modulus of the condensate field. And this should be compared with this one. So essentially what happens is that these structures are washed out by the quantum fluctuations. But qualitatively, not too much big difference. I agree. You know, it's very hard to say what exactly this Pauli blocking does to your effective potential. Of course, it kills certain fluctuations. That's clear. And that's probably why you have here much more structure, so to say, in the large coupling limit here, as compared to this one here. But we were amazed ourselves that the strong coupling was not that bad after all in this context.
Okay, thanks.
Daniel, is it quick?
I hope so. It's certainly naive, very naive question, Andreas. You're simulating these 4 fermion systems, so you have a theory at a critical point on the lattice. Can you extract perhaps information about a function?
About?
So the spectral function of your critical fermions, right? Do they have an ordinary Kellen-Lehmann representation in terms of a spectral function? And if so, how would that look?
Yeah, so if you talk about the same, different people mean different things by spectral function. You mean those which you use in linear response, I guess, right?
Well, it's just it's a way of so the technical definition in terms of yeah,
but yeah, but this usually is not completely trivial on the lattice because of Euclidean time if you're talking about the same spectral functions. So we haven't looked at these spectral functions.
Yeah.
No.
I mean, I would say in principle, yeah, it's information that we'd like to get, but it's certainly from my perspective with a different lattice formulation, it's technically challenging, but I think it's something ultimately we'd like to do. I agree, except it contains important information.
Yeah.
It breaks my heart to close a session where my own, we're so closely related to my own work, but we really have to go to Gather Town to continue now.